Hello everyone. The title of the talk is Key Role of Temperature Function in Calculating Quantization Dimension. Temperature function that arises in multifractal analysis in fractal geometry plays a key role in calculating quantization dimension of the associated probability measure. Speaker Mrinal Kanti Roy Chaudhary. Today is June 14, 2025. What is quantization? Quantization for a Borel probability measure refers to the idea of estimating a given probability by a discrete probability with support containing less number of elements. It has broad application in signal processing and data compression. Classification of quantization. Constrained quantization has recently been introduced. After the introduction of constrained quantization, quantization theory now has two classifications: constrained quantization and unconstrained quantization. Unconstrained quantization, which traditionally in the literature is known as quantization, is a special case of constrained quantization. This talk deals with unconstrained quantization, which sometimes in the sequel will be referred to as quantization. What is quantization error? Let P be a Borel probability measure on RK, equipped with a metric D, induced by norm this on RK, and R is a positive real number. Let alpha be a locally finite subset of RK. That means intersection of alpha with any bounded subset of RK is finite. This implies that alpha is countable and closed. Then the distortion error for P of order R with respect to the set alpha denoted by VRP alpha is defined by this formula. The nth quantization error is infimum of all these kinds of error, where alpha is subset of RK and cardinality of alpha lies between 1 and n. We assume rth moment that this number is finite. Then there is some set alpha for which the infimum occurs. That is, we can replace infimum in this formula by minimum. Such a set alpha that does not contain more than n elements is called an optimal set of n points for P. Remark: if the support of P contains at least n elements, then an optimal set of n points contains exactly n elements, and they are the conditional expectations in their own Voronoi regions. Because of that, in unconstrained quantization, an optimal set of n points are also referred to as an optimal set of n means, provided that the support of P contains at least n elements. Remark: if the support of P contains infinitely many elements, then the nth quantization error VNRP forms a strictly decreasing sequence. The number DRP, which is limit R log n minus log VNRP, where VNRP is the nth quantization error and R is the number that was defined before. If this number exists, it is called the quantization dimension of order R of the probability measure P. The significance of the quantization dimension is that quantization dimension measures the speed, how fast the specified measure of the quantization error converges as n tends to infinity. A lower quantization dimension suggests a faster convergence of the nth quantization error. For example, if you look at these two pictures are for two different probability distributions, pictures of nth quantization error. If you observe, see that here quantization error is decreasing faster. Here it is decreasing also, but slowly. So in this picture, the first picture, or for the first probability measure, quantization dimension is lower. Here in this picture, quantization dimension is higher than the quantization dimension of the probability measure defined in the first picture. High quantization dimension means decreases slowly. It is extremely difficult to calculate the optimal sets of n means for a Borel probability measure. On the other hand, to calculate the quantization dimension, it is much more easier. Indeed, it is not necessary to know the optimal sets of n means in order to compute the quantization dimension of a Borel probability measure. Observation. For an absolutely continuous probability measure, quantization dimension equals to the dimension of the underlying object. It does not depend on R. For a singular continuous probability measure, for example, for a probability measure supported by a fractal, the quantization dimension depends on R. Because of that, it is highly interesting to investigate the quantization dimensions of the probability measures supported by fractals. Graf and Luigi first determined the quantization dimension of self-similar probabilities with open set condition. That is, there is no overlap in the similarity mappings. Under the open set condition, Lindsay and Mauldin determined the quantization dimension function dr, where r is a positive real number, of an F conformal measure M associated with a conformal iterated function system determined by finitely many conformal mappings. They established a relationship between the quantization dimension and the temperature function of the thermodynamic formalism that arises in multifractal analysis of the measure. Here is the paper of Graf Luigi, the quantization dimension of self-similar probabilities. And here is the paper of Lindsay Mauldin, quantization dimension for conformal iterated function systems, published in Nonlinearity. Observation. Subsequently, under the open set condition, M. K. Roy Choudhury determined the quantization dimension of some other fractal probability measures. For each probability measure, it has been seen that if the quantization dimension exists, then it has a relationship with the temperature function of the thermodynamic formalism that arises in the multifractal formalism of the measure. So it was also shown by Lindsay Mauldin in this paper, quantization dimension for conformal iterated function systems. So quantization dimension of self-similar measures by Graf Luigi. Let Sj be contractive similarity mappings on Rk with similarity ratios Sj for here j equal 1 to n. There are n mappings are there. Satisfying the open set condition. What is open set condition? That means there exists a bounded non-empty open subset O of Rk such that these two conditions are true. And let P1, P2, Pn be a probability vector and mu equal to this. So mu is the self-similar measure here generated by the similarity mappings and this probability vector. Let kappa be the unique positive real number such that this is true. If this probability vector P1, P2, Pn is equal to this, that is if D is the similarity dimension, then Graf Luigi showed quantization dimension of the measure mu equal to kappa and equal to D. That means quantization dimension does not depend on R. But if the probability vector is chosen in such a way that it is not equal to this, then quantization dimension of the self-similar measure mu is equal to kappa, where kappa is given by this formula. So that means kappa quantization dimension depends on R, where R is a positive real number. Let us now generalize this result. Quantity dimension of measure satisfying bounded distortion property by M. K. Roy Choudhury. Let Sj be contractive mappings, similarity mappings on Rk with similarity ratios Sj satisfying the open set condition, which was defined before. Here is the open set condition. Let E be the unique non-empty compact subset of Rk such that this, that means E is the limit set of this iterated function system of the similarity mappings. For sigma, which is sigma, that is sigma is a word of length n, where I equal to 1 to n, denote E sigma means S sigma E. What is S sigma E means composition mappings. S sigma means a composition mapping S sigma 1, S sigma 2, cycle S sigma n. Let me be a Borel probability measure on Rk satisfying the boundary distortion property. What is it? That means there exists a constant k such that for any 2 sigma tau belongs to this, any 2 words, this is true. Mu sigma tau e less than k of mu sigma e, mu s tau e, and yet it's k inverse in this. Then mu has support the limit set e, of course. It can be proved. The pressure function PQT, now topological pressure is coming to calculate the quantization dimension. It has been seen that for several fractal probability measures, quantization dimension have been exactly determined. And each case, there is a pressure function. So here the pressure function PQT is this one, is given by this. Which is continuous, strictly decreasing, and it can be shown that this limit exists. And this limit is, this function PQT is continuous, strictly decreasing, and convex in each variable separately. Moreover, for a given q, if limit t goes to plus infinity, PQT is minus infinity, and limit t goes to negative infinity, PQT is plus infinity. That means the graph of PQT looks like this. Notice that for a given q, if q is fixed, there exists a unique number t, which is of course depends on q. Here I think it's beta q. T equal to beta q, for which pq t equal to 0. That means pq of beta q equal to 0. Beta q is, so for a given q, this beta q is unique, for which pq comma beta q equal to 0. Beta q is continuous, it can be proved. Beta q is continuous, strictly decreasing, and convex. Beta q is commonly called the temperature function of the thermodynamic formalism that arises in multifractal analysis of the probability measure mu. In the next slides, you will see how this temperature function helps us to calculate the quantization dimension. That means the relationship of this function with quantization dimension. You will be able to see the next 2 slides. If q equal to 0, so we know pq beta q equal to 0. Now suppose put q equal to 0. Then p of 0 beta 0. So q is 0. So pq beta q means p0 beta 0 equal to 0. Here. So what does it imply? Implies that j equal to 1 to sj beta 0 equal to 1. That is beta 0 equal to how is the dimension of the set E. How it comes? So if you here pq t formula is this one. So if you plug q equal to 0, then from here after simplification, you will get this. So this is the definition of how is the dimension of the limit set E. And so the P of 1, 0, what is P of 1, 0? Again, if you plug here Q1 T equal to 0, then we get P10 equal to 0. So that means, so this one says for each Q, there exists a unique beta Q for each Q beta Q equal to 0. That means from here we can say beta 1 equal to 0. let 0 less than r is a fixed number, positive real number, then the quantization dimension kappa r of mu is given by this. It has been proved in that paper. Or it can be proved. Then the quantization dimension kappa r of mu is given by this. Now, let us now compare this formula with this one. So write QR equal to kappa r over r plus kappa r. Then if you compare that with with the pressure function, you see PQR RQR equal to 0. Because in the pressure function, if you compare with this expression, PQT is this one. So if you compare this one with this one, then if QR equal to kappa r, then you get PQR RQR equal to 0. And we have seen this kappa r is the quantization dimension. Now look how kappa r is connected. So kappa r equal to, so then PQR RQR is 0. That's comparing the equations we have, beta QR equal to RQR. RQR is this. And notice that kappa r equal to RQR by 1 minus QR, which is beta QR by 1 minus QR. So this is the standard formula. That means quantization dimension is connected with the temperature function. So here is the graph. So here all these results you can pictorially represent by this graph. So y equal to RQ line and QR 1. How to dimension? Y equal to beta Q curve. To determine dr, which is a quantization dimension, first find the point of intersection of y equal to beta q and the line y equal to rq. Then dr is the y-intercept of the line through this point and the point 1, 0. See that there's an interesting connection. So if you know beta q curve, then yrq, find the point of intersection, then take 1 and this point 1, we have seen this is 1, 0. Then join these 2 points, extend it where it cuts the y-axis, that is the quantization dimension. If k equal to 1, okay, now from this result, we are going to deduce graph logic result. How? If k equal to 1, put k equal to 1 here in 1. Where is 1? Here in 1. K equal to 1. Then all these expressions, so there are this equal to this equal to this. That means we get mu of s sigma tau equal to mu s sigma e mu s tau, mu of s tau e, where sigma tau belongs is two words this. Hence, if we write mu of sj of e equal to pj, then by 3 for any omega belongs to this, we have mu of s omega e equal to p omega 1, p omega 2, p omega 3, like this, p omega, which is p omega. Hence, by the multinomial theorem, we have this expression. What is this? If you look at this formula, see that here. So this expression, this one, sum omega belongs to R and mu e omega s omega kappa or r plus kappa. This expression looks like this. Now put this value, put this sum, that is this expression, here. So this one reduces to, this is equation number 2, reduces to this one. Then 2 reduces to this one, which is equal to 0, of course. Then implying this one. So if you see n and n cancel, so limit is gone because there is no more n. So this that means this is equal to 1. Remember, this is equal to 0. So 0 is missing here, implying this is equal to 1. Because log of this part, n cancel, so limit is gone. So log of this part equal to 0. There is a typo here because 0 is missing, implying. So now take out the log. So this is equal to 1, which is the formula that Graf-Ruzsky used to calculate the quantization dimension of a self-similar measure. Notice that kappa equal to r k 1 minus q r beta k 1 minus q r is also true here. That means including Graf-Ruzsky, Lindsay-Moldin, and Rai-Chaudhury's results everywhere where quantization dimension of a fractal probability measure is known, it has a connection with the temperature function. There is an open problem. Now, for a general fractal probability measure, if the quantization dimension exists, whether such a relationship also exists, this relationship also exists, is not known yet. This is a long-term, interesting, and significant open problem. Thank you.